Good afternoon, all of you. My screen is visible.
Good afternoon, sir. Yes, sir.
Yeah. We'll see that third unit, principle of phase control converters. In this, there is a different subtopics. Anyhow, I will show the introduction portion in that. There is a single phase and three phase controllers based on our load requirement, whether we have to proceed with single phase or a three phase. Suppose the load is high rating, we need to go for three phase. And here, this is the different in the case of semiconductor drive subject and this subject. In our case, each controller will connect the load. So load is R load or RL load or RLE loads. In our case, in a power electronics case, we'll use only the loads R, RL, RLE loads. And whereas in the case of drive subject, directly will connect as a motor, whether it is a series motor or a separately excited motor or induction motor or a synchronous machine, like that. So that is the difference between these two subjects, and there is one freewheeling diode is there, and another concept is effect of source inductance. In this case, normally supply is connected to the controller. In the all other cases, supply will be the pure supply. There is no source effect, but practically speaking, we need to consider the source effect also. Source consisting of a resistance and then reactance and all. So that is a inductor effect. We'll consider that. And dual converter. Yesterday I mentioned that there is a, based on the quadrant operation they classified, no, there is a first quadrant, two quadrant and all, but just a minute, somebody is waiting. See, who is Manasa? You must join with your college mail ID, Amma. Manasa. There is a dual converter. This is a 4-quadrant converter. As we know that fully controlled converter is a 2-quadrant converter, half controlled is a 1-quadrant converter, and whenever we require all 4 quadrant, you must use as a dual converter. This is nothing new, only by combining two fully controlled converters in anti-parallel, it will form as a dual converter. That's all. So one full control converter will give 2 quadrants, another full control converter will give another 2 quadrants. So therefore all 4 quadrant is possible in this. So this is based on a AC to DC. DC is a variable one. And now fourth unit, two parts. One is a DC to DC, that is what chopper and all. DC to DC we call it as a chopper. There is a different types of choppers are there. Step down chopper, step up chopper, up and down chopper, and the control techniques are there. Different control techniques we'll discuss in this unit. Normally in the rectifier also, what is the control techniques? In the rectifier we'll use firing angle control. By changing the firing angle, it is going to be control. Whereas in the chopper case, there is a duty ratio control that will be on time to total time. The ratio between on time to the total time, we call it as a duty ratio. Del will notation anything, that is the duty ratio. So for that, there is a control strategies are here, time ratio control and current limit control. So in each controller, there is a control techniques will be there, like a rectifier or a chopper or inverter or anything. We require control techniques to control the output voltage. So to get variable DC, we need to make use of control technique. And there is a types of choppers, another topic. All is very small things and simple things. And there is a type A, type B, type C and E. So there is a different types of choppers. So we'll see that based on type A is a first quadrant, type B is a second quadrant, type C is a first and second, type D is a first and fourth, type E is all 4 quadrant operations. So like that. So here you may get the doubt, application side you will use only the DC machines only, but in the phase control rectifiers also we will use DC motor is one of the application. But the thing is there, if the input is AC is available, you cannot use the chopper. So that's why whenever input is DC, like a solar power or fuel cells or batteries, something like, we can use as a DC to DC converter. So that is a chopper. But input is AC, you want to operate as a DC machine, then you can connect as a phase control rectifier. That's what depends on availability of the source. You can choose whether it is a phase control rectifier or a choppers. So chopper means input is DC. Phase control rectifier means input is a AC. Another one is there is a natural commutation. In phase control rectifier we use as a natural commutation. But whereas in case of choppers we'll use as a forced commutation, because supply is a DC supply, it never go natural. Another one is regulators. There is a buck converter, high frequency operations, all these things same as above, step up, step down, up and down. No? Similarly there is a buck converter, boost converter, SMPS and all will use here. So buck converter, boost, buck boost converter are regulators. This is about the half of the fourth unit. Next half is AC to AC converter. So this one is a DC to DC, and next half is a AC to AC converter. So principle of operation of single phase cycloconverter. Here there is a classification. Cycloconverter again divided as a based on the connection wise. We can say that midpoint cycloconverter and bridge type cycloconverter. The difference of these two things, whether in the phase control rectifier also, based on the connection, we divide as a midpoint controller and bridge type controller. Means transformer will be used there, and bridge type we don't require any transformer. That is the advantage. If you not use the transformer, then automatically performance will be improved there, because if you use transformer, there is a transformer losses also come into the picture. And here also cycloconverter, based on connection we divide midpoint cycloconverter and then bridge type cycloconverter, and based on the level, frequency levels, step down cycloconverter and step up cycloconverter. So up means free output frequency more than the input, down means output frequency less than the input. And another one is a AC voltage controller. This is also AC to AC, as I said in the lab class also. In a cycloconverter it will variable frequency controller, this will be variable voltage controller, and frequency will be remains constant. And for all the cases these are the loads we need to connect. Same circuit, you connect the R load and you see the performance. Anyhow, all these things we'll see in the practically in the simulation circuit also. I will show you how to change the load and what is the performance and what is the difference in the waveform, all these things. And RL load case, load is replaced with RL. Instead of only R, you can connect another L in series with the R, and we'll see the performance. So what is the difference and all we can notice. That is the second half of the unit 4. And final one is a unit 5. That is a principal operation of a single phase inverters. Here we'll get it as a two types of inverters, means half bridge and full bridge. That is all related to bridge inverters. But normally in the olden days we have series inverter, parallel inverter and all. Even our lab also we have that experiments. The only the difference is here commutating elements. Suppose why commutating elements is required in an inverter? That will be required only in case of inverter and then choppers, and other circuits we don't require, because these two are in the forced commutated circuits. And here you can see that forced commutation input is a DC. That's why base to turn off the switches we required as a forced commutation. So in that forced commutation, what we have is commutating elements L and C. So when you are connecting commutating elements in series with the load, that type of inverter I call it as a series inverter. So commutating elements are connected in parallel with the load, that is a parallel inverter. So and third type is this one, bridge type inverters. This is half bridge and full bridge. Half bridge means output will be the half of the input, and full bridge you will get it as a full output voltage. So that is the types of inverter here in case of series inverter, I mean half bridge and full bridge for the bridge type. And then like chopper case, there is a voltage control techniques I told, no, time ratio control and current limit control. These are the two methods in to control the output voltage. Similarly, in case of inverter also, there is a voltage control techniques are there. And this voltage control techniques, two types. One is a internal control strategy and external control strategy. So external means after getting the output voltage of inverter, and you can use combination of the controllers to change the output voltage. That is the one aspect, but that will leads many number of controllers need to use. But whereas internal control technique, that is a PWM technique, pulse width modulation techniques. In that there is a division again, sinusoidal pulse width modulation or single pulse width modulation, multi pulse width modulation and sinusoidal pulse width modulation. Like that, different techniques are available to control the output voltage of a inverter, and this is the pulse width modulation technique. And now this based on the source side, we can say that single phase inverters and three phase inverters. So this one is single phase inverter, and here from this there is a three phase inverters are there. In the three phase inverter, again voltage source inverter and current source inverter, two types of inverter based on the source voltage. Suppose source is having fixed voltage, that we call it as a voltage source inverter. Means impedance offered by that source is a negligible, whereas impedance offered by the source is a large impedance, then that we call it as a current source inverter. There is a lot of differences are there in voltage source inverter and then current source inverter. That's why one important question is here, the comparison of VSI and CSI. VSI is nothing but a voltage source inverter. Normally we'll use voltage source inverter, and current source inverter will be used high rating applications and all. But for each drive, suppose we want to control one induction motor, if you use the current source inverter, each induction motor we need to connect one current source inverter. But whereas if we use voltage source inverter, the group of drives, or you can say that parallelly we need to operate many number of drives at a time, we can use as a voltage source inverter. Like that, there is a different advantages, disadvantages individually it is there. That we'll see under a case of comparison of VSI and CSI. Another one is a three phase bridge inverter. Again same as rectifier case, single phase rectifiers and three phase rectifiers. Similarly, in the case of inverters also, single phase inverters and three phase inverter. Three phase inverter, two modes of operation. One is a 180-degree mode of operation and 120-degree mode of operation. This is a firing pulse durations. If you give pulse is 180 degree, that will see that what is the line to line voltage, because all these things are in three phase. No, if you give input is a DC supply, you will get output is a three phase AC. And if I operate 180-degree mode of operation, what is our line voltages and phase voltages? If I operate 120-degree mode of operation also, we notice what is the line voltage and phase voltage, and what is the difference of these two modes of operation, and how many devices will conduct at a time. So all we can observe while I am operating as a 180-degree mode and 120-degree mode of operation. All these things you can able to do simulation also. Whatever topics are explained just now, all the things is possible using as your simulation software, that is a MATLAB. And these are about the syllabus. And now we'll see today's presentation agenda. Again, introduction of individual controllers in depth a little bit, and then power semiconductor devices. What are the devices? That is in the first unit we see, no, IGBT, MOSFET, BJT and all. And then power electronics converters, types of converters introduction I will explain here. And then advantages and disadvantages of a power electronic, and then applications of power electronics. This is just basics of this thing. And we'll see that as we start the introduction, first thing is definition. So I already mentioned in the previous class, how can you define as a power electronics? So it is only will do two things, control and conversion, that's all. So any controller you can take it, whatever may be the load you can connect, the function of that controller, whether you can convert AC to AC or DC to DC or DC to AC or anything, but that I call it as a conversion. Not only the conversion, in addition to that, in each controller there is a control technique. So that control technique will give the output variation. That means whether you can use pulse control or duty ratio control or PWM technique or anything, that will, based on your control technique, your output is going to be controlled. That's why you can say that power electronics defines as a control and conversion of a large amount of electric power. So why I used as a large here, because all power electronic deals with the high power rating. So that is the definition of a power electronics. And as you know that why control and conversion is required. This is the thing will do the power electronics, but why it is? When you take any application, let it be fan application, whether control is required or not, or conversion is required or not, you can identify. In our house there is a fan, and here both things are required. Control is required, conversion also required. Why control? Control means speed control. Sometimes you maybe need higher speed or sometimes lower speed or like that, medium speed, whatever you want, you can able to control your fan. That's what the control. Then why conversion is required? Conversion, let you think that available supply also AC, fan also AC, then why? Because to control the speed, we required as a voltage variation. That's what the conversion, that is a AC to AC conversion is required. Input also AC, but output also AC. If I am not controlling that or converting AC to variable AC, then your speed will be constant. That is the reason we require. Not only that, any application if you take it, we required both control as well as the conversion. So now we can see that any application, let AC supply is available. If I am using as a loads something, these are the different types of loads. In nowadays all electronic equipment, the voltage levels are different. Even in computer also you may be required different voltage levels in the inside all these things. So because motherboard is different, something floppy disk, so very like this. So you can see that voltage regulation, microprocessor controller is there, a LED light, or there may be motors, different small motors and all. So in the output side you can see that, our application side, you may be required 3.3 volts or 5 volts or 12 volts or 9 volts or whatever, different voltages are required. DC only, but all the DC appliances may not be the fixed voltages. What we need, you want to operate as a 12 volts motor, you need 12 volts DC. Or LED is there, you need 5 volts or something else voltage, different voltages. But now you have as a AC supply, let it be whatever may be the voltage. Let us assume that 100 volts or 220 volts or 230 volts, whatever you may have. Let it be, that is also controllable. So now once you have a AC some amount, what you want to do is you have to convert from AC to DC. If input is DC, then what I have to use here? Anybody? If input is DC, what I have to use here? Here I have to use as a chopper, DC to DC. But now input is AC here. That's why I used as a regulator, that is a phase control rectifier at moment AC to DC converter, and now that DC voltage is given to the chopper. Suppose we are using that some fixed amount, or let it be if we use as a diode rectifier, let us assume that. What will happen? If I use diode rectifier, fixed DC will get it. This is a from AC to DC. If I use diode rectifier, fixed 24 volts will get. If you give 100 volts input, let us assume that some voltage you get it in the output is a DC. Let us assume that 24 volts. But now this 24 cannot be connected to the LED or a 12 volts motor or something microcontrollers or something. So again I want to convert this 24 volts to some different voltages. So now I can use in each appliance you can connect as a one chopper. So this is a DC to DC. If I use instead of diode rectifier is a phase control rectifier here, so I don't want to use this. Directly I can control the alpha, whatever voltage you need, that you can connect it to the corresponding application. But whereas here is a diode rectifier used. So this is the one sort of thing, control and conversion. Conversion is required. That's what I am explaining this. And another one you can see here, in the olden days and all, the regulators will be like this. In fan regulators, once if you see old days regulator, or maybe in our college regulators also, some of the classrooms will be like this only. So that means what is inside in this, if you open this, there is a resistors. How many steps? Maybe this is 1, 2, 3, 4, 5 or something. 4 steps or 5 step is there. So there is a steps of resistances are connected. So all resistance are in series. So now if you keep that position 1, so means one total resistance is in the connection. So based on your value of the resistance, and drop will be created, rest of the voltage only connected to the motor, to the fan motor. So in that you will get one speed, but I want to increase the speed of a fan. Then what I have to do, you will move this to some other one more step. So let it be you are moving like this. Then what will happen? The one of the resistance is going to be cut off. All 5 resistors are in series. You are cut off in one of the resistance. Then what will happen? Value of the resistance is less now. Then drop will be less. Then more voltage will pass through the motor. Then motor speed will be high because voltage is directly proportional to the speed. Again, if you move one more step, another resistor will cut off and so on. If you do like this, finally if you come to that position 5, then what will happen? All the resistances are cut off and only direct voltage is connected to the motor. Then speed of the fan will be high, and that is the case. And what is the drawback in it? Because of the resistor, there is a power dissipation is going to take place. Now if you see that regulator also, under some cases little bit heat also will be developed. If you touch that something, some heat dissipation is going to be takes place. So that is the problem actually, and to overcome that problem, nowadays regulators are like this. So what they will do, some regulators are like this, smooth variation is there, and some regulators in this also they made it as some steps. So here steps and here both is same only thing is they taken as a tapping some point of angle. So here smooth variation 0 you can start and you can rotate like this up to 180 degrees. If you keep 180 degrees, then we will get the 0 speed, something like that. Initially it will be 180 degrees, then you are reducing the alpha, speed will be increases. So here also you will take the different tappings. Alpha will be 180 and then 140, 160 and 90 and then 0 something. So then what will happen? If I keep on changing the step, instead of smooth variation, they made it some steps and you can move that. Some particular alpha will be there and corresponding voltage will connect it to the machine. And if you open this, there is a AC voltage controller will be there. Nowadays regulator and olden days regulators, if you open, it will be there only the resistors, some not in our small lab resistors, there is a little bit power resistors will be there, some round shape, some thick, more something like. So if you open, you can see also that is the resistors. But now if you open, here is a triac, one device will be there. For that, small firing circuit is connected, and that is a variable, whatever at what instant you want to pass that alpha value, you can pass it automatically. Fan speed is going to be controlled. So this is the all these reasons, that's what I am telling now here, why the conversion is required. So for this purpose we require as a conversion. So this normally the power electronics consisting of a majorly three portions, nothing else: source, load, in between as a controller. So we can see that there is a power electronics controller. This controller may be anything among the five. This is the PE controller. So whether it is a rectifier or a chopper or inverter or AC voltage controller, anything, this is in this side there is input and this side there is a output. So this is the normal setup. Wherever you can see that, suppose the load is a DC motor, let us assume that, just for example I am telling. So this is a DC motor load. Then what is the input? Let us assume that AC supply is available with you. Then what is this power electronics controller? This will be as a phase control rectifier. Suppose input is a DC, then this could be as a chopper. And similarly, if this is a induction machine, let us assume that, then input is a AC. Then what I have to do? If input is AC, induction motor input also AC, but I want to control the speed of a induction motor, then AC to AC variation is required. That means either you can use AC voltage controller or a cycloconverter. And some cases input is a DC, but I need to operate a induction motor, then you can use as a inverter, like this. So depends on our requirement or load requirement, you can connect in between whatever types of power electronics converter is required. And now you can see that there is a, in the power electronics converter, a lot of components are there. The major component is a switches, that is whether it is a SCR or a BJT or a MOSFET, and some cases energy storage elements, because I know for commutation purpose and all, and control function, because for that power electronics controller, power circuit is there as well as the control circuit also. I told no, what is the control circuit? We need to provide as a firing pulse. So for that, control circuit also required. And there is a flow of power, that's what the applications, all the things, we can see that different types of, by seeing this you can able to understand power electronics will be there in the all the areas. You can see that renewable energy integrations. Suppose there is a solar is there, I want to convert that power or feed that power to the grid. How will you feed to the grid? There is a solar power is a DC. Now we have to use as a inverter. So it's to convert DC to AC. That AC you are feeding to the grid or directly to the any particular load. So like that, anything you can take it. Heating elements, that is induction heating, and a light control, fan control. So in the light control also you can see that in the olden days, suppose if any light is there, directly either on and off, completely glow or completely off. But now if you see the some of the restaurant and all, there is a dim light and all. So what they will control the illumination. So that's what the same, if you pass the less voltage, automatically voltage illumination is going to be controlled. So energy conservation systems and power electronics in the transportation systems, and then transmission systems, and then power systems case. So lot more drive applications. So many areas, this power electronics controller will be the more impact on that. And now a majority of the applications, the switching the power flow. So what we are doing is finally, I already mentioned in first class itself, throughout the application or throughout the subject, we will only the switching actions, that's all. So once we switching on and switching off the duration, automatically you can able to get your control output but efficiently it will happen because power loss in these components are very less when compared to any of the conversion. Suppose we want to use a potential divider, let's assume that. What is the function of potential divider? There is a input is a DC supply. You use as a rheostat in between input and output. You want variable voltage in the output. If I use as a rheostat, what will happen? Automatically voltage will be drops in that and remaining voltage is connected to the load. You will get the variable DC voltage if I use as a potential divider or a rheostat. But what is the drawback? Simply power dissipation. The output is connected to some of the load. The load draws the current. That current pass through the for what you call it as rheostat. Then automatically power dissipation is going to be takes place. So, but whereas here, if I use any control technique, AC voltage controller or anything, then automatically switching losses are very minimum. That's why efficiency of that controller is going to be high. Then we can see that power switches, whatever we are using, all the things are in power switches. Now in the first unit we'll discuss only the power electronic switches. So BJT, diode, as well as BJT, MOSFET, IGBT, these things we'll discuss in that area. That's what I mentioned here: diode, BJT, MOSFET and IGBT. And whenever we are using combination, that is IGBT. So power MOSFET and power IGBT has a large role to play in modern power controller, because IGBT is a efficient device for all inverter application. Generally we'll use as IGBTs, but in our home inverter is there, we can see that normal small rating of less than 1 kVA rating of inverter and all, they will use MOSFETs rather than the IGBT, because these are cheaper the things. Ratings also less, because our inverter rating is small, then we can use as a MOSFET. And we can see that impact on that IGBT and all in this unit. And now, so in the olden days, normally there is a power electronics is a rapid change is there, but still also is a lot of research is going on in the power electronics. The lot of technology is developed. It is there in the last 50 years, but due to advancement in the technology, decades, the cost of the devices as well as the reliability of the device and applications, all the things are improved. So cost will be minimized and reliability will be improved, and then industry application and commercial, aerospace and residential, military. So many applications nowadays power electronics are used. And then it involves the semiconductor devices and then converter technologies. So that will be applicable to the machine control, means drive control applications and all. And then there is a further development is there in the AI techniques, then fuzzy logic, artificial neural network, for all the cases that incorporated in the device technology improvement and then control strategies. Nowadays AI technique and fuzzy logic controller are used to generate the firing pulses. So that pulses, when compared to conventional pulses, what we are using in the conventionally, suppose I want to fire the SCR, let assume that. To fire the SCR, we required as a firing pulse. In normal case, to generate the firing pulse, op amps and all use integrated circuits we are using, and we are generating as a firing pulse. But nowadays we don't use any of the integrated circuit, op amps, resistors, capacitors to generate the comparator and all. We use op amp, no. So now that we don't do. Directly, either we are writing in microcontroller code or AI technique, we can use it, or fuzzy logic algorithm, we can use it, or artificial neural network, anything. We will generate directly as a firing pulses through this algorithm, and that will dump to that of the system, and automatically you can able to generate that firing pulses is connected to the gate and cathode of the each device. So like that. So these are the some of the equipment will be used in the system, that is a controller. There is a small inductors, resistors, capacitors, switches, fuses, and small rating of the transformers, and there is a devices like MOSFET, BJT, IGBT, like that ICs. So these are the components preferably we are using in that. And the SCRs, now we'll come to the SCR part. In 1957, SCR was introduced, and later the other devices has been developed with advancement in the semiconductor technology. This semiconductor technology is improved, and that's what the reason you can see in mobiles also. 10 years back, mobile weight, and nowadays mobile weight and all size, and then features, all these things. This is all about the semiconductor technology only, and this is the actual device. If you buy in the outside market, so this is the SCR. If you see this terminology, this side there is a gate. You can see this one is a gate. Based on here, you can see this crossing point onwards. If you see, this terminal is a gate, and this one is a anode, and this one is a cathode, because you cannot connect reversely or something, because by seeing this, this is a small gap here, they will cut something like this. That is the order. From that onwards, gate, anode, cathode. So normally in all the circuits, whatever you will represent, this is the symbol. This is the actual device, and this one will be as a symbol. Anode, there is a 3 terminal 4 layer semiconductor devices. So there is a anode, cathode and gate. Anyhow, that will come under again in the that unit, second unit completely, characteristics and all, and diodes also there, different types of diodes. So anode, cathode only will be there in the diodes, but SCRs we required as a 3 devices. And then power diodes are available in this rating. You can see that 3000 volts and 3500 amperes and up to 1 kilohertz of frequency, switching frequency. So whereas in the thyristors also 6 kV, 3.5 amperes and 1 kilohertz of frequency operation thyristors ratings are available. This is the reason, as I mentioned, no, suppose I want to operate higher voltages or higher current, one device rating is this one. Then if you want to operate more than this rating, what you will do, you have to connect a number of SCRs or in series or in parallel. And then you can see that BJT rating, here rating will be voltage rating, current ratings are less in case of BJT, but switching frequency is high. You can see in the case of SCR and all, only 1 kilohertz switching frequency, and here switching frequency is 10 kilohertz. Switching frequency means on and off, no time intervals. A very faster rate it is going to be on and off, but voltage ratings, current ratings are small. So this is the symbol. Any of maybe company, these numbers may change, depends on your type of BJT and all. You can see here there is NPN transistor and then PNP transistors. These are the some of the components we can use like this. And then MOSFET, there is a low range of approximately 1000 volts and 50 amperes. This is still lower current rating, but frequency is very high frequency. Whenever you required very high frequency application, will use as a MOSFET than the BJT and all. And this is the symbol for BJT, the source, drain and gate. So based on this curve, we can start the representing that names of the or terminals to that particular MOSFET. And there is a N channel MOSFET and P channel MOSFET. All in-depth construction, all the things will become under first unit itself. N channel enhancement type, and then P channel enhancement, and then depletion layer type. All these things will become under. These are the construction. Also, we'll see that how the device is going to be fabricated, what are the layers need to place, and what will happen, and how it will be formed. All these things will come under that. And then IGBTs. IGBT is a power rating 1200 volts and 400 amperes and 20 kilohertz. But here you can see IGBT is formed by combination of the MOSFET and BJT. We are using as a input side, this one is a MOSFET and output side is a BJT, that will combinedly get it as a IGBT. So these are the combination of input side is MOSFET will use and output side is a transistor, that combinedly will form as a IGBT. So in between in latest IGBTs and all, there is a feedback diodes also we can use it under we are using as RL load condition and all. So that depends on type of IGBT and all. So anyhow, this combination of MOSFET and BJT will form as a IGBT. So that's what I told. No, here there is a diode, inbuilt diode will be there. That will be feedback when our switch is off state, and whatever energy stored in that elements, it is going to be dissipated through that diode. So that is the reason feedback diode is on the olden days. What we'll do is IGBT is there and we will connect one anti-parallel what you call it as diode. But now the latest IGBT is directly inbuilt with that of diode is coming. Directly we can buy that IGBT and we can design your inverter also. There is a DC input is there. We can design your inverter and you convert it into DC to AC. That AC you can connect it to the application. So input is instead of DC, you can use from the solar panel. You can do project like that. You buy small rating of solar panels and you design your inverter and control technique. One of the latest control technique you can use it, either microcontroller or any of the AI techniques you can use it and generate the firing pulses. You give that pulse to that of the IGBTs and IGBTs will fire, means inverter will operate. It will convert DC to AC. That AC you can use it or you can feed to the grid. So that is what things you can do it. And these are the controllers, as I already mentioned you. Uncontrolled rectifiers that will convert AC to the fixed DC. Here uncontrolled means that our output will be fixed. That is only the difference. Means fixed AC, fixed DC. But whereas this is a phase control rectifier, these are the controllers I am telling, all 5 controllers. So if we consider diode, that will be the 6th one. But we don't consider that is a controller because it is a fixed one. And AC to DC means phase control rectifier. And DC to DC means chopper, and this one is a AC voltage controllers. So this is what is the function of AC voltage controller. It will convert fixed AC to the variable AC with constant frequency. That must be remembered, constant frequency. And this is a cycler converter. What will happen this, there is a AC to AC only with variable frequency. So voltage will be vary and frequency will be vary. And last one will be the inverter. So only these controllers, other than the first 2 introduction means devices. First unit completely BJT, MOSFET, IGBT. So anyhow, some of the basic information is known to you. We'll start directly SCRs because that is the more important throughout the subject. SCRs will start in the second unit. After that, we'll go to the BJT, MOSFET, IGBT. Then only we'll start the controllers. So that is the sequence we'll follow. And then diode rectifiers, as you know that there is a different types of diode rectifiers also there, but function is it will convert AC to the fixed DC. So that is the major function of a diode rectifier. The input voltage may be single phase or a 3 phase. I told no, if we need more output voltage or high rating of application you want to run, preferably input must be as a 3 phase AC supply. Otherwise, it is a single phase AC supply. This will be used in the electric traction or battery charges. These are the applications actually. Traction application and battery charging application and power supplies and welding application and UPS. In our house we have no UPS there. Normally AC supply will be there, and then there is a battery means before that there is a diode rectifier will be there. It will convert AC to DC and then it will charge and then it is connected to as a inverter. That is the sequence. Now you can see the rectifier operation is very simple. What will happen is input is AC supply and output will be as a DC. I used here is a small one diode, just half wave rectifier. So half wave rectifier only positive half cycle it is going to be controlled. Now you can see that positive half cycle. You can see here when during positive half cycle, what will happen if this is the positive half cycle? Once this point is there, diode will be forward bias. If diode is forward bias, what will happen? Current is passing like this. If you know the current waveform, we can easily notice that how it is going to be controlled. So now here you can see this will be positive half cycle. Current is passing through the diode and it is getting like this. But during negative half cycle, you notice that it won't go because switch is open. Switch is open. That's why during negative half cycle it is coming up to this point and it will be stopped. So that's why I mentioned here forward bias condition and reverse bias condition. Forward bias condition, it is switch is closed, and reverse bias condition diode is open. So that is the reason you are getting output only during the forward bias condition. This is your output, and during negative half cycle output will be 0. So that is the diode function. If you want to use the bridge type of diodes, means many number of diodes, or three-phase diode rectifier, all the things you can use it. Whatever instead of thyristors, if you use diode, it will be fixed. Whatever output you are getting, that will be fixed one. But whereas in the case of thyristors, you will get it as a different voltages. Now this is the half wave diode rectifier. Same thing, just we'll show the waveforms. Waveforms are very simple. What I want to draw is, you see the first one, you can observe here. What I want first supply, let it be input voltage based on the turns ratio. This will be magnitude, maybe less or more, depends on that. Let it be whatever input is given, that is your input. So what is the input of the rectifier? AC. That's why I drawn as a AC. So some cycles you can draw. One full cycle explanation is sufficient. From that full cycle onwards, next cycle is going to be repeated. What is this? 0 and pi, and this one is a 2 pi. Up to 2 pi is one full cycle, and cycle will be repeated. This from this onwards repeated. What next? I want to see that once thyristor is on during positive half cycle, what is our output? I want to draw the output. Once it is on, when it will be on during positive half cycle. This is a during positive half cycle. What is our output voltage? If I draw a voltage waveform here, same as the input, because we started it is a diode. That's why whatever you are getting input, that will get it as a your output. This is your output. And during negative half cycle, it is a reverse bias. Output will be 0. That's all. This is your load voltage waveform. So this is your output. So now I want to see the any current waveform. Suppose I want to see the current. So what will happen? It is a load, is a resistive load. So current waveform is same as the voltage waveform, but magnitude will be reduced because of some value is there in the load. Current I is equal to V by R. Whatever voltage we are getting here, that divided by value of the resistor. So current waveform also like this. Some magnitude will be reduced, and again it will be 0. And again positive half cycle. Cycle is going to be repeated. So like this. So these are the what to call it as different waveforms. Now you can see positive half cycle. I mentioned same as the source voltage waveform. This NVM means based on the number ratio. Suppose if we reduce here, will get reduced. If it is more, will get more. But let's consider this 1:1 ratio. Whatever input is there, that will be here. That is appear in the load side. And this is the current is divided by R. So whatever we are using as a R load current, that is equal to voltage by R value. So here R or N somebody used. So you can use directly R. So that is a easy conventional. This is a V by R, that will give. But what is magnitude is saying that Im by N means this turns, because of the secondary turn. So forget about the turns. 1:1. We just make it as a 1:1 means output current is equal to V by R. That's all. That is the magnitude. Similarly, for negative half cycle, what will happen? This will be 0. And current also will be 0. Because device is open at pi. And then cycle is going to be repeated. So this is the very simple logic. Seems to be waveforms are 3. But if we go to power electronics controllers and all, you need to draw more number of the waveforms. But logic only. So here you can notice that very simple logic during positive half cycle and during negative half cycle. So during positive half cycle, what will happen? Diode will be forward bias. You will get the output voltage same as the input voltage. During negative half cycle, output voltage will be 0 because diode is open. Similarly, current side. During positive half cycle, voltage and currents are in phase because resistive load. That's why if it is inductive load, current waveform will be modified, but voltage waveform is same. And that way, we can see that this will be as same as this, but magnitude is little bit less comparatively this. So that is the thing. Now we'll see that another one is phase control rectifier. Whatever we noticed in the previously, that will be as a diode rectifiers, devices, all these things. Now phase control rectifier, what is the function of phase control rectifier? Anybody? As we discussed all the 5, no, that function. So phase control rectifier, it will convert AC to variable DC. That is the function of the phase control rectifier. AC voltage to the variable DC voltage. Then rectifiers line voltage for their commutation. That is what the line commutation or a natural commutation. Why it is a line commutation? Because input is a AC supply, and to turn off the device, we must bring current pass through the device to the 0. That is the reason without using any additional circuit, supply itself it goes to natural 0 every pi, 2 pi and so on. That's what we can represent, what you call it as 0 instant. It is going to be open. That is a natural commutation or a line commutation. This is a line or natural, both are same, I told you. So then it is maybe fed from a single phase or a 3-phase source. So based on your load rating, you choose single phase controllers or a 3-phase controller. It is mainly used for the DC drives. Metallurgical and chemical industries and all will use only the conversion, and variable DCs will be used. And excitation of the synchronous machine and all, field excitation we require as a DC supply. No, for that case also we can use. Even in our case, speed control of a DC motor, there is armature control is there, flux control is there for variable voltages. So now the excitation want to change in the field side, what we require? Variable voltage is required. Then use this, we can get it as a variable voltage for the excitation of synchronous machine and all. But the synchronous, alternator and all, we required as excitation. And these are the classifications of a phase control rectifier. First, phase control rectifier is dividing as two things. One is a single phase converter, another one is a 3-phase converters. So again, the single phase converters is dividing as two things. One is a half wave control rectifier, another one is a full wave control rectifier. Again, full wave control rectifier is the same as 3-phase also. 3-phase also half wave control and full wave. But again, full wave controller is dividing as a based on the connection of the controller. There is a midpoint or a center tapped converter. Another one is a bridge type converter. Similarly, in the 3-phase also same. And again, the bridge type we divided as a two things. So one is a semi converter, another one is a full converter. So these are the, again in the case of 3-phase also, semi converter and full converter. So these are the major classifications. If this chart is completed, that means your third unit will be completed. That's all. And in addition to that, 4-quadrant operation is there. That is a dual converter. One more topic. So that means single phase controllers we need to discuss, as well as the 3-phase controller. Single phase we dividing like this. So this portion, once you are aware this, similarly 3-phase also same as that. That's why a little bit more number of questions will get in this part. But only if you know the answer of one question, the rest of the questions only the modification. You don't need to read once again or do something. Only thing is, what is the difference between these half wave to full wave? That's all. Or R load to RL load, or RL load to RLE load, like that. Only little bit comparison wise we can able to draw the waveforms, but circuit and all only simple things. And now this, instead of what you call it as diode, now I used as a thyristor. Previous circuit and this circuit different is only this. Earlier is a diode. Circuit is same. Maybe I use transformer there. It's not required. Directly can give the supply and we'll get it as this. And previous waveforms I will draw here. This is the input something, and then output will be like this, 0 output, and voltage waveform, and similarly current waveform. This will be 0 and this is a current. So these are the voltage and current. And now the difference is, instead of starting here, you need to control where you want to start. That is decided by you. At that instant only you pass the pulse. That's all. That is only the difference. That's what diode and thyristors are exactly similar except the starting point. Whereas in the diode, starting point will start only 0.7 volts, something like that. No, it will start from 0 onwards. And now for thyristors, even though if it is a forward bias from 0 onwards, but you want to fire the device, at what instant you want to fire, you provide the pulse at that particular instant. That is the reason you require one firing circuit. That circuit will generate the firing pulse based on your requirement. Suppose if I say I want to fire that pulses at an angle of 30 or 40 or 60 or anything, if you say, at that instant only it is going to be 5. That is only the difference. Now we'll see the waveforms are very simple. As usual, supply, we are giving supply is AC supply, Vs, that is Vm sin omega t. And now you have to provide the firing pulses. Something I want to show the firing pulses. I will show the pulses will be like this. I want to give the pulse at an angle of 30 degrees, something pulse. Negative half cycle, reverse bias, we don't require any pulse. And then positive half cycle only I have to give the firing pulse, because these two, negative half cycle from pi to 2 pi, it is a reverse bias. Thyristor is a reverse bias. When thyristor is forward bias, anode is positive with respect to cathode, then only thyristor is forward bias. That will be happen only during the positive half cycles. That's why I am providing the firing pulses to the that. And now we can see the output voltage waveform. When it will start conduction, maybe from 0 onwards it is a forward bias, but conduction means switch will be closed only at an angle of alpha. That's why from this point onwards device is going to conduct. If device is conduct, output is what? Same as source. So what is source? This one. So say from on point onwards will represent same as the source is your output. That's all. And negative half cycle 0. And again from 2 pi to 2 pi plus alpha, this I call it as alpha. Just rough only, nothing is worry. Anyhow, that unit will cover only to understand something. And now we can see from alpha only you have to give the firing pulse. No, this is alpha, means here 2 pi plus alpha. The same gap you have to maintain. Whatever alpha you are providing here, that is for all the cycles. If you want to change, you can change it. Instead of here, I want to shift here, somewhere here, you can move this also somewhere here, like that. So now you will get your output voltage will start here and end it with pi. Every pi, 2 pi, 3 pi and so on. Current is natural 0, switch will be open. Again during negative half cycle 0, again positive half cycle it will be like this. So this is the voltage waveform. How will you get the current waveform? Same only, but magnitude will be little bit reduced. That's all. So this is positive only, this one, and again 0, again this. So like this is 0 only. So now this is the voltage waveform, output voltage. This is output current. If I want to draw voltage across the device also, when it is on, what will happen? It is off, what will happen? On means 0. Wherever it is on, you keep zeros. Wherever if it is off, keep same as source. From this point it is off, no, I kept source. And from here it is on, 0. And this portion is off, then same as source. So means this only I drawn, nothing else. Then again 0. Then again same as source, like this. So that is your 0. Then source voltage. This is the voltage across the door, like that. So very simple. What I mean to say is, now we can see if switch is closed means I want to give the firing pulse. Whenever if you give the firing pulse, then only switch is going to be closed. Now I am providing the firing pulse. Where I want to provide? Only during positive half cycles. Negative half cycles will be 0. And again, we can see that output voltage from 0 to alpha, pulse is not there. Wherever pulse is there, only it will conduct. Once it is conducting, pulse is not required. It is only to turn on the device we required pulse. Once it is on, how to turn off the device? It has to wait until current pass through the device is 0. That's why it is continue to conduct up to pi. But once pi reaches, due to natural commutation, this will be open. During negative half cycle, automatically 0. And again positive half cycle, it will be repeat the cycle. So this is the output voltage. This is the output current. This and this is exactly same, only magnitude is reducing. And this is the voltage across the device VT. Across this I am measuring with respect to anode, and you can see that from 0 to alpha device is off state. That's why you measure the same as source will get it. That's why I drawn same as source. And the small gap I mentioned, whether you want you can use it, otherwise you can make it as a 0 only. That gap is voltage drop across the device when it is conducting 1 volt or 2 volts, 1 to 1.5 volts normally. We don't use to show that. Normally you can keep 0 also. Strictly speaking, you want there is a small voltage drop. You can make it 0. And once device is on means what is voltage across this? It is short, no? That's why voltage across that will be 0. That's all I made it 0. And here is off state, no? Off state means same as source. Wherever it is off, you can keep same as source. Up to off duration, you write as such source. And if it is on, short it. Off source, like that. This is the voltage across the device. And this is the sequence you can represent as a thyristor. Previous one is a diode. This one is a thyristor. You can easily see that difference between the diode as well as the thyristor. So because you can control here, instead of starting here, you want to start here, you will get this is the output. That's all. And still you reduce, this is the output. Like that. You are able to controlling by passing the gate signal instant. That's all. So anyhow, we'll see in the next class all other comparisons, and then that introduction will close maybe next class or one more class, then we'll start actual. And if you have any doubt, you can ask me. Otherwise, you can leave.